Hello dear students, welcome to the channel and welcome to this playlist of instrumentation and sensors in which we have discussed about different types of instrumentation, different applications of different instrumentations. We saw different sensors, their working in detail. We saw the sensors based on applications. We saw analog and digital sensor classification, and we recent times we were watching the measurement uncertainties in which we were visiting different type of errors. So this class is going to be in continuation to the previous class in which we discussed the different types of error and how to get rid of those errors or how to solve those errors. So I insist that you check out the previous class as well in order to understand today's class better. So for that, the link will be flashing on the top right hand side corner of your screen and the I button, so you can click on it and you can check out that class. And now that's out of the way, let's get started with the type of errors. So in previous class we have seen the systematic errors in detail, and today we are going to see the random errors in detail. So random error in measurements are caused by unpredictable variations in the measurement system. That means the variations which are not predictable, right? And they are usually observed as a small perturbations of the measurement either side of the correct value, either positive or negative, right? So that error occurs in a approximately equal number for series of measurement made of the same constant quantity, and because of that, then random error can largely be eliminated by calculating simple average of the number of repeated measurements which are provided at the measurement quantity remains constant during the process of taking repeated measurements. So the averaging process of the repeated chapter can be done automatically by intelligent instrumentations, and the degree of confidence in the calculated mean or median or range values can be quantified by calculating standard deviation of the way or variance or of the data. So these are the parameters that we are going to discuss today, and how they affect these different type of errors. So let's get started with that. So let's say the statistical analysis of measurement subject to random errors. So the first would be the mean and median values, and this one is quite simple. It's a simple mean or simple average, and the average value of the set measurement of the constant quantity can be expressed as either as the mean value or the median value. And as the number of measurements increases, the difference between mean value and the median value will become smaller. But for any set of n measurements, say let's say it's going from x1 x2 to xn for constant quantity, the most likely true value is the mean value. Okay, and I think I don't need to show you the formula for the mean value. It's simple average value formula, and this mean value will be valid for all the data sets where the measurement error are distributed equally about zero error value, which means where the positive errors are balanced in quantity and magnitude with the negative errors. Okay, so average was pretty simple. Now let's see the median, and the median is approximately to the mean that can be written down without having to sum the measurements. Okay, so the median is the middle value when measurement in the data sets are written down in ascending order of magnitude. For a set of n measurements x1 x2 up to xn for constant quantity, which can be written down in ascending order of the magnitude, right? So median value can be given as x median is equals to x of n plus 1 divided by 2. Simple. So let's see it with an example. Let's say for this set of 9 measurement which goes from x1 to x9 are arranged in order of magnitude, then the median value would be x5, right? The middle number, right? How do I know it? So I have values till x9, so x9 plus 1, what would it be? X10. X10 divided by 2 would be x5. So the median value would be x5. Now for an even number of measurement, the median value in the in midway would be between the two center values. For example, let's say we have 10 measurements going from x1 to x10. The median value will be x5 plus x6 divided by 2. So which two are the middle values? X5 and x6. Now you have to take average of them, in simple words, right? Take two middle values and take average of them, or take the mean of them. So suppose the length of the steel bar is there is an example which we are going to do now. So let's say we have a steel bar which with a length measured by number of different observers, and the following set of 11 measurements are recorded in millimeter. And let's call this measurement set A. You can see it consists of these values: 398,420 going till 413430. Okay, now we have to find the median and mean value with the help of these formulas, formula number 3.4 and formula number 3.5. So when you find the mean would be 409, and when you find the median would be 408. But now suppose that the measurements are taken again using a better measuring rule, and with the observers taking more care to produce the following measurement. We have the measurement set B. Okay, and measurement set B goes from starting from 409, then 406, 402, 407, 405, 404, 407, 404, 407, 407, and 408. Okay, now you have been asked to find the mean value. See here, it was ranging from 396 or 394 till 430. Okay, so the range was too big and the inaccuracy was too high. But here we are having almost accurate results which are ranging from 402 to 408 only. Okay, so now you have to find mean and median. So see, here we have the mean is 406 and median is 407. So which of two measurement sets A and B uh, and the corresponding mean and median values should we have most confidence in, right? Which values do you think would be more close to the actual value or true value? So intuitively you can say that measurement B or measurement set B has more reliable quality because measurement are much close together. In set A, what happened? The range was going from 396 to 430, right? Which means the value of the range will be 34, while in measurement set B it was going from 402 to 408 only. So spread was only 6. So the smaller the spread of the measurement, the more confidence we have in the mean or median value which we have calculated. So always consider that. Now let's see one more example. What will happen if we increase the number of measurement by extending measurement set B to 23 measurements? Okay, what will happen if we increase the number of measurement by extending measurement set to 23 measurements? So we will take 23 measurements, or we will ask 23 people to take measurements. and let's call it measurement set C, and let's try to calculate mean and median one more time. And again we are asking that them to uh, be precise and be more accurate while taking the readings or taking the measurements. So again the mean is 406.5 and median is 406, right? So it is confirming our earlier statement that median values tends towards the mean values as the number of measurement increases. Now let's see the standard deviation and variance. So expressing the spread of measurement simply as the range between largest and smallest value is not in fact a very good way of examining how the measurement values are distributed above the mean value, right? So what is the better way of expressing the distribution of the calculation of variance or standard deviation of measurement? So the starting point for calculating these parameters is to calculate the deviation or error di of the each measurement xi from the mean value. So what would we do? Let's say if I have to find the value, the deviation for each and every individual value di. So what would be di? It would be into the mode 409 minus 406.5. Okay, so 2.5 would be di1, again 0 0.5 would be di2, and so on. So here we have the simple formula. Di would be xi minus x mean. So xi would be this present value, this is our mean, you have to take the subtraction of it. Now then the variance would be given by whatever measurements you took, starting from d1 to dn, take squares of them and then collectively add them, right? And then take n minus 1. So if you have 23 measurements, then divide it by 22 and it would give you variance. And when you want the standard deviation, which is also holds the sign of sigma, then simply take a square root of the variance. Okay, it will give you the standard deviation. So under root d1 square plus d2 square up to dn square. Now let's calculate the sigma and v for the measurement sets A, B and C above. So here is the question. Mathematically minded readers, okay, not here, here. The question is calculate sigma and v for the measurement sets A, B and C, and measurement sets A, B and C we have here. This is the measurement set C, this is measurement set B and A. So we have already have the mean and standard mean and median for both of them. Here median would not be required, let's put it aside, and we all also have uh, di for each and every set. So what will we do first? We will take measurement and then we will calculate the deviation. So here we have the measurement for set A and we have the deviation. Okay, so and how do we get minus 11? So the mean was 409 and measurement was 398. So what did we do? We took the subtraction of measurement minus mean, and by that we came to this values. So here we have the deviation, then we squared them. So that it doesn't matter if you have a minus in it or if you don't have it, because we are either ways we are going to take the square of it, so minus will fade away. Then what you would do, then you have to sum the square of the deviation, and n again number of measurement 11, and minus 1 it would be 10, and when you take the sum of the deviations, then you would find 1370 is the sum of deviation. So V, the variance would be 1370 divided by n minus 1. What was the n? 11. 11 minus 1 would be 10. So your the variance would be 137. And when you try to find the standard deviation, when you take the square root of this value, you will find standard deviation is 11.7. Same way as we are going to calculate the deviation, standard deviation and variance for set B. Here we have it. Again, deviation would be the subtraction of 409, this first value, minus 406 plus 3, then 406 minus 406, 0, 402 minus 406 minus 4, and so on. And then you will take squares of them, and then using this formula for variance, you will find variance. The variance would be 4.2 and standard deviation would be 1.05. Same way as you can find for C as well. C has more values. I'm not going into details of that, but the variance for C would be 3.53, and sigma would be, or standard deviation would be 1.88. So now please note that more close we have the value to the true value, the value of standard deviation goes more close to 0, right? See, the smaller values of V and sigma for measurement set B compared with A corresponds with the respective size of the spread in the range between maximum and the minimum values of two sets, right? Understood? That means as V and sigma decreases for a measurement set, that means we are able to express greater confidence that the calculated mean or median value is close to the true value, right? So lesser or smaller the value of V and sigma, more confidence you would have, or your value or your measurement would be more close to actual value or true value, so that the averaging process has reduced the random error values close to 0. Now comparing the V and sigma values for measurement sets B and C, and V and sigma are getting smaller as the number of measurement is increasing. So it is confirming the confidence of the mean value increasing as the number of measurement increases. So we have observed for so far that the random errors can be reduced by taking average or mean or median of number of measurements. So however, although the mean of the or median values is close to the true value, it would only become exactly equal to the true value if we could arrange an infinite number of measurements. So always keep that in mind. And as we can only make a finite number of measurement in practical situations, the average value will still have some error every single time. So this error is quantified as the standard error of the mean. Okay, it's called standard error of the mean, which we are going to discuss now. But before that, subject of graphical analysis of random measurement error required to be covered. So let's first see that. So the graphical techniques are a very useful way of analyzing the way in which random measurements are distributed. And the simplest way of doing this is to draw a histogram. So we will be drawing a histogram in which bands of equal widths across the range of measurement values are defined, and the number of measurements within each band is counted. Now see this image. It is a histogram of set C of the length measurement data given in upcoming section. Let me show you. In this section, which means basically histogram of the mean median values of earlier three. So it is showing the bands chosen are 2 mm wide, And for instance, if there are 11 measurements in the range between 405.5 to 407.5, so the height of the histogram for this range would be 11 units. See, also if there are 5 measurements in the range from 407.5 to 409.5, so the height of the histogram over this range would be 5 units again. See, so the rest of the histogram is completely in similar fashion, and such a histogram has the characteristics of shape shown by truly random data. So with symmetry above the about the mean value of the measurement, as it is actual value of measurement error that is usually the most concern, it is often more useful to draw the histogram of the deviation of the measurement. So here you can see it holds the highest value between 405.407. It holds the highest number of measurements from 405.5 to 407.5, which means it must be the value which is close to the actual value. But it also means this is the value which uh, most of the people who are taking measurements have found. So as it is the actual value of the measurement error that is usually of most concern, it is often more useful to draw the histogram of the deviation of the measurements from mean value rather than to draw a histogram of the measurement themselves. So the starting point for this is to calculate the deviation of each measurement away from the calculated mean value, and then histogram of deviation can be drawn by defining deviation bands of equal width and counting the number of deviation values in each band. So the histogram has exactly same shape as the histogram of the raw measurements, except that the scaling of horizontal axis has to be redefined in terms of the deviation values. So let's see what happens to the histogram of the deviation as the number of measurement increases. As the number of measurement increases, smaller bands can be defined from the histogram, which will retain its basic shape but then consist of a large number of small steps in each side of the peak. So in the limit, as the number of measurement approaches infinity, the histogram will become smooth curve known as the frequency distribution curve. Okay, so that's why you're always being asked that try to take as more number of measurements as you can, so that you can minimize the error as much as you can, right? Now to ordinate this curve is the frequency to occur of the each deviation value and the abscissa of the magnitude of a deviation. So this figure is has this histogram figure and this frequency distribution curve figure. They are about the zero deviation value, which is very useful for showing graphically that the measurement data only has random errors. Although these figures cannot easily be used to quantify the magnitude and distribution of the errors, but very simply graphical techniques do achieve this, and we are going to discuss that. So if the height of the frequency distribution curve is normalized such that the area under it is unity, then the curve in the form is known as probability curve. See, and the height fd at particular deviation on the y-axis holds the deviation magnitude d, which is known as probability density function or pdf. So the condition that area under the curve is unity can be expressed using this formula: integration minus infinity to infinity f of dd equal to 1. Then the probability that the error in one particular measurement lies between two levels d1 and d2 can be calculated by measuring the area under the curve contained between two vertical lines which are drawn through D1 and D2, as you can see here. See this vertical lines D1 and D2 in this area, which have been overshadowed, right? So this can be mathematically expressed using this formula. So instead of infinity, you are taking a certain area going from D1 to D2. Now, for particular importance of assessing maximum error likely in any one measurement is cumulative distribution function, or CDF. And this is defined as the probability of observing a value less than or equal to D0, and mathematically it is expressed using this formula. As you can see here, we are going from minus infinity to D0, and let me show you that area. It's going from here to here, right? So the CDF is the area under the curve to the left of the vertical line through the D0 value. Now, deviation magnitude dp corresponding with the peak of the frequency distribution curve. As you can see here, the peak is called dp, and it is the value of deviation that has greater possibility, right? If the errors are entirely random in nature, then the value of dp will be as close as possible to 0. If it is entirely random, then it would be 0, equal to 0. And for non-zero values of dp, it indicates systematic errors in the data in the form of bias that is often removable by the recalibration. Now let's see one more distribution type, Gaussian distribution. So if you have a measurement sets that only contains random errors, they usually confirm a distribution with a particular shape, which is called Gaussian. So although this confirmation must always be tested, it is not always necessary that if it is a random, then it would be Gaussian, but there is a higher possibility, right? So the shape of a Gaussian curve is such that the frequency of a small deviation from a mean value is much greater than the frequency of a large deviation. And what do I mean by that? So it would be more clear when you see the curve itself. See, this is the Gaussian curve, right? So does that statement make sense now? Now let's see the statement one more time. Let's revisit the statement. So it says the shape for Gaussian curve is such that the frequency of a small deviation from the mean value is much greater than the frequency of a large deviations, right? So see, it's more close to 0. Now the this will coincide with the usual expectation in the measurement subject of random errors, that are number of the measurement with a small error is much larger than the number of measurement in the large error, right? In simple words, you can say the number of measurement in the small errors is much larger than the number of measurement with a large error. So there are alternative names of Gaussian distribution. It is also called shaped distribution. It is also called normal distribution. And a Gaussian curve is formally defined as the normalized frequency distribution that is symmetrical about the lines of zero error, and in which the frequency and magnitude of quantities are related by this expression. I'm not going to say that out loud, but you can understand it. So here m is the mean value of the data set x, and other quantities are as defined earlier, standard deviation, pretty easy. So this equation is particularly useful for analyzing a Gaussian set of measurements and predicting how many measurements lie within some particular defined range. If Measurements deviations d are calculated for all measurements like such that d is equals to x minus m. Then the curve of a deviation frequency plotted against the deviation magnitude is a Gaussian curve known as the error frequency distribution curve, and the mathematical relationship between fd and d can be derived by this equation as you can see here. Now the shape of Gaussian curve is strongly influenced by the value of sigma, and with the width of the curve decreasing as the sigma becomes smaller, as a smaller sigma corresponds with the typical deviation from the measurement from the mean value, and as it becomes smaller it would confirm the earlier observation that mean value of a set of a measurement gets closer to the true value as the sigma decreases. So if sigma is used as a unit of error, the Gaussian curve can be used to determine the probability that deviation in any particular measurement and Gaussian dataset is greater than the certain value. And by substituting the expression for f of d into the probability equation, the probability that error lies in a band between error levels d1 and d2, you can express this using this equation. See, we are taking the area d1 to d2, and here we have pretty much same, except what did we do? We took the differentiation. So solution for this expression is simply by substituting z is equals to d by sigma, and the effect of the change of error distribution curve in new Gaussian distribution it will have the standard deviation of 1, which means sigma's value will be 1, and the mean of it will become 0. So this new form is known as the standard Gaussian curve, and this standard Gaussian curve is shown in this image here. See, so this standard Gaussian curve depends on a variable called z instead of d, and the equation for this standard Gaussian curve is shown here, but there is a catch. Unfortunately, neither of these equations can be solved analytically using the tables of standard integrals and numerical integrations, which are provided only method of the solution. But in practice, the medium of a numerical integration can be avoided when analyzing the data, because standard form of equations like this equation and its independence from the particular values of the mean and standard deviation of the data means that the standard Gaussian table and the tablet fz for various values of z can be used. So let's keep today's class till here. We will see the standard Gaussian tables in upcoming class. So if you have any doubts or queries related to today's class, please mention them in the comment section below. If you have any suggestions for me for particular chapter or particular subject, please mention that in the comment section below as well. And if you have any type of feedback related to the channel or videos or playlist, please mention them as well. All type of feedbacks, whether they are positive or negative, all type of feedbacks are welcome. And uh, if you are attending, then please comment if you're liking the way of presentation or not, if it requires modifications or not. Okay, so we will keep today's class till here. Next time we meet, we will be discussing the standard Gaussian tables in detail, and then we are going to uh, basically we are going to take the whole picture of errors and considering the solution of that error. Okay, so until next time, keep revising, Thank you very much for listening. I'll be meeting you next time with a new topic. Thank you very much for listening and goodbye for now.